Okay, so in this particular problem, it says consider two blocks with masses m1 8 kilogram, m2 which is 2 kilograms. They are attached to each other by a string which passes over a massless and frictionless pulley. Okay, so it tells us here m1 is sitting on the table and that there is friction, and then the coefficient of static friction, which is 0.34, the coefficient of kinetic friction, which is 0.18 here. All right, so here's M1 that sits on a rough table, and then M2 is hanging. So let's crack A, B, C, and D out. Part A asks us to find the magnitude of the static frictional force on M1. But the important condition given here is that it says when the system is released, it is observed to remain at rest. So while there is a hanging mass, nothing is moving, nothing is happening. All right, so let's go ahead and find the static frictional force correctly. So listen to part A here, which I hope to prevent misconceptions moving forward. All right, in order to do so, let's go ahead and good rule of thumb is to draw out your forces that's acting on each of the block, where and when appropriate. So this is f of g for M2. There's tension in the string. In this case, I drew f of g and t the same length, aka the same magnitude, because the system is not moving. It suggests that the forces must equal in magnitude. They just are pointing in opposite direction. Well, for M1, there's also a tension. If the system is to move, there is a tension causing M1 to accelerate to the right, but that force is in the string. That's also called tension. And here there's only one string or one rope that's just wrapped around a pulley, and the mass of the pulley here is assumed to be massless, so we don't have to worry about those physics conditions for now. Okay, so there's T there, which is the same T here. And then there's the force of static friction. It says it's not moving, so the frictional force here would be F of static, which is subscript S, not K. And then I drew the force of static friction here in blue, the same length as T. Because it's not moving, T must equal the F of static in magnitude or length. All right, so let's do it. The proper way to do part A is what I'm about to do, okay? Which I hope you listen well so that you don't do wrong physics. In order to do so, it asks us to find F of static. So the first thing I want to do is focus on M1. The reason I want to focus on M1 rather than M2 is because F of static here touches M1. M1 is the one sitting on the table, so it experiences static frictional force. So I'm going to start with M1, okay? So I can just set up Newton's second law for block 1 on the table. So here I wrote net force on M1, which is equal to M1 times acceleration. If they were to accelerate, they would have the same acceleration, so I don't need any subscripts for acceleration. However, I can go ahead and introduce the forces exerting on M1 in the line of motion. So here I have T that would pull M1 to the right, but at the same time, there is a force opposing it, which is F of static here. So I'll just do T minus F of S. I subtract because F of S is acting against the block's tendency to move right in this diagram. And A I highlighted here. A is 0. So in the next statement, I will substitute A, which is equal to 0, because it says the system remains at rest. So while nothing is touching it, the system is not moving, which implies that there is friction holding the system stationary. Okay, so M1 times 0, which is 0. So here we can just solve for F of S by moving to the other side. So negative F of S gets moved to the other side, which just becomes F of S. Again, M1 times 0, which is 0. So you can cross that term out. So really you have T minus F of S is equal to 0. And I just move negative Fs to the other side so I can get rid of that negative sign. So here we have F of S is equal to tension, which makes sense, right? The system's not moving, so these two magnitude have to equal. They're just opposite. And that's a true statement. All right. Now, I don't know what T is, though. Okay. The goal of part A is just trying to find the force of static friction that's keeping the system stationary based on the masses given. I don't know what T is, but what I can do is now set up the physics for M2, the hanging block. For M2, the weight of the box naturally wants to pull it down. But here in this case, T is going to act against it with equal magnitude, which is to keep it at rest. So therefore, I can go ahead and set up F of G minus T, which is equal to M2A. And if I do this properly, M2A is going to be 0 because the acceleration is 0 again. And then f of g minus t, well, in this case, I need to know what t is, because on this side, in order to find f of s, I need to know what t is. So this is just a quick substitution. F of g is equal to t, and then now we can just substitute f of g for m2g. Okay, you have to be careful which m you're using here. The work here is for m2, so the f of g here must be for m2, which is the hanging mass in this first diagram. All right, and that's that. We know that t is equal to m2 times g, so wherever t is on this side, we can go ahead and substitute it in quickly. All right, so we can say that f of g2 is equal to f of static, which in this case makes sense. So before I move on, it's important that you recognize that you can look at the system as a whole. If you look at the system as a whole, tension here, watch where my arrows go, the tension there and the tension here will always cancel because they're equal and opposite in magnitude. So they naturally will cancel if you look at the system as a whole, okay? So therefore, really, there's only two forces acting on the system. It's f of g2. Therefore, we can say f of g2 must equal to f of static, which I just proved here in my work. m2g is literally f of g of the hanging block, which is m2, and that must equal to the static frictional force that's preventing the system from moving. So all this work is just to prove that you can look at the system as a whole and that t will always cancel out in the work if you look at the system as a whole. Okay, so that's up to you how you want to do these types of problems. I would just go ahead and get on with the statement, for like MCQ questions. Okay. Therefore, we know M2 in this case is 2 kilograms. The acceleration due to gravity is 9.8. Here, we use a positive 9.8 because the question asks us to find the magnitude of the static frictional force. But it's up to you. It doesn't really matter. I would just find magnitude and then use common sense and tell, whether it's positive or negative based on the direction of motion. All right. Therefore, F of S here would just be 19.6 Newton. And so that would be your answer for part A. Okay. What I do want to point out is a big misconception that folks might carry over. Some might do part A using this function here. They might do part A using f of static is equal to coefficient of static times f of n. Well, then this would cost you a whole lot of wrong answers, okay? You might be tempted to plug in mu s, which is 0.34 because it's given, okay? So you might get suckered into using this particular function because the coefficient of friction is given. But I'd like to point out that you should not. So why this function is correct, and you can substitute in mu k for 0.34, and here f of n is just the weight of m1. So watch my cursor. The force of static friction here exists between the m1 and the surface. So m1 is going to have a weight, which is f of g1, but as the weight of the box m1 pulling it down, there is a contact force pushing it up, which is f of n, but f of n for m1 in this case is just the weight of m1. So I can substitute f of n for the weight, and weight is just m1 times g, okay? And then I know what the weight is, which is 8, or excuse me, the mass is 8. I know what the acceleration due to gravity is 9.8. So if you follow this strategy, you would have gotten an answer of 26.7 Newton, okay? And you would totally be wrong, okay? While the function is correct, this is not the work that you need, okay? So I like to point out this is a big trap setup for you. This is a big misconception. Know what it is that you need to find. So f of static is a reaction force, okay? F of static is a reaction force. When you do it this way, what you just found is the maximum static frictional force that exists on this particular system. This is the maximum force, but you don't always need the maximum value, okay? So this is a big misconception. So I said here, this is the maximum static force that you just calculated, but keep in mind, you don't always need the maximum static frictional force to keep systems stationary, okay? So you don't need max. Okay? So hopefully this graph helps reiterate this concept. The force of static friction can start at 0. So just because you push doesn't mean objects move. You have to push hard enough to exceed it, okay? So here in this graph, the force of static starts from 0 and it goes all the way up to f of s max. So if you did this function on the right that I did the misconception for, you would have gotten a value of 26.7. But to keep a system stationary, you don't always need max. It can be any value from 0 all the way up to 26.7. In this case, we found that value that's needed to be only about 19.6 Newton. Okay, so keep in mind, force of static of friction can vary between 0 all the way up to the maximum value. But you don't always need max. So don't use this function. Don't use this function just because it's there all the time. So you have to understand what's being assessed of you. All right, I hope that makes sense. Okay. Therefore, let's go ahead and move on. Part B. Part B now said if the two blocks are now switched, where M2 is on the table now and M1's hanging, it says calculate the acceleration. So let's crack this out. I'm going to draw my free body diagram, F1G here. T I drew a little smaller than this one because it's going to accelerate, implying that the tension has to be just a little smaller than the weight here. Otherwise, it would stay still again, but it's not. Tension here is the same. So here's T and T. There's only one string, so I didn't use subscript. And then here, the F of static, excuse me, the F of kinetic coefficient now, okay, or the F of the kinetic frictional force. Excuse me if I can find my words. The force of kinetic friction here in blue is a little shorter than T. Now that it's moving, it cannot equal to the same magnitude. It has to be a little smaller. And then I label this as F of K because it's now moving. So to find the acceleration, I'm just gonna look at the system. As I stated earlier, learn to look at problems as a system in order to find acceleration really quickly. If you look at the system, the T's here in the string will naturally cancel out because they're pointing opposite. This one's pointing right, but if you open the system up, or if you stretch the system horizontally, this is pointing left, so it acts against each other. So really what's causing the system to accelerate downward is the weight of M1. What's acting against it? It is the kinetic frictional force due to the surface of the table onto M2. So hence I have FG1 minus F of K. Again, the direction here is already taken care of for you with the negative sign. I can break F of K into F of N, but F of N would be now the weight of M2 because remember, the blocks are now swapped, okay? So M2 is now on the table. M2 is going to push down the table, which has a weight, F of G2, but because it pushed down, there's a contact force on the table, from the table onto the box, which is F of N. So I can replace F of N with FG2. In that case, F of G2 can be broken down into mass 2 times gravity, and then you can just plug in all the values. M1 is 8, G is 9.8, minus the coefficient kinetic friction is given here. Here's 0.18. M2 is 2, G is 9.8, and then the total mass here is 10 because 2 plus 8 is 10. Okay. If you simplify stuff on the left side, you'll get 74.87, and then to find A, divide both sides by 10, so the acceleration is 7.487 meters per second squared. That's for magnitude, so that's your answer. Part C. To do part C, you have a couple different strategies. I'm just going to focus on M1 to start. It doesn't really matter. That's your choice. I'm just going to start with M1. To find the tension, I'm just going to look at M1. So here's the weight of M1 that's causing it to accelerate down, but at the same time, there's the tension pushing or acting against it. So I'm going to set up net force for M1. Therefore, net force is broken down to two vectors. The weight of M1 minus the tension acting against it, which is equal to M1. Here, I can just, excuse me, move T to the right side. That makes it a positive. And then M1A gets moved to the left side of the equal sign, which changes sign. Here I know everything. M1 is 8. G is 9.8. M1 is 8. The acceleration we found already is 7.487. If you simplify that, you should get a value of 18.5 newtons. It asks for magnitude, so I leave that at assist. Now, in case it makes you happy, you can use the perspective of M2. What would cause M2 to accelerate is this tension here in red. What's acting against this is F of K. So if you set up Newton's second law for M2, you do T minus F of K, but make sure you plug in the right mass, so this would be M2. All right, to solve for T, we move the negative FK to the right side and mix it a plus sign. And then from here, we can break up F of K into mu K F of N. But F of N now is just the weight of M2 because M2 is the one resting on the surface. For this particular problem, I left out the units here because I'm running out of space. M2 is 2, A is 7.847, mu K is given. F of N is now just M2, and M2 being 2 times G, which is 9.8. So if you do that correctly, you should get the same value of 18.5, okay? All right, let's do part D real quick. Part D asks you to find the time it takes to fall 10 meters. So I'm just going to use my displacement function. It's assumed to be released from rest, so I'll go ahead and cross out VIT because VI is assumed to be 0 here. My displacement, I'm going to use -10 because it's falling down. It's up to you. If you want to treat the line of motion to be positive, then plug in 10. If you treat the line of motion to be positive, then the acceleration will be positive. It's entirely up to you. So here, just for kicks and giggles, I'm just going to say delta y is -10 because it fell down, quote unquote down. And then if I treat this direction as down, then the acceleration is also going to be negative. Okay. The acceleration we found already is 7.487. If that's the case, we can simplify the right side. 1/2 times -7.487, which would be -3.74. And then we can just divide both sides by -3.74 to get t squared, and then to get t, we square root both sides. That'd be the answer. Okay, and that is your answer. But as I stated earlier, if you want to, which I do, you can treat the line of motion to be positive. Watch my cursor. So M2 is moving to the right, and then M1 is going to fall down. So that curvature there is in the positive direction. So if you do that, then delta y would be +10. But then the acceleration will also be positive. So really, we're just playing with negative signs here. Do whatever you like. I like to leave out the negative signs in my work. I did it here just in case you're that kid that goes, well, it's, M1 is moving down, so shouldn't the vertical displacement be negative? Well, the answer is yes. But if you choose this to be a negative direction, then you have to be consistent with your acceleration. Then your acceleration will also be negative. Otherwise, you will have to take the square root of a negative number, which would not work out. That would be imaginary. Okay. I hope that helps. Stay nerdy. Don't be whack.